So, let us for starters just look at one of the simplest radiation detectors that you can think of, a so-called Geiger counter. Or rather, let's not so much look at it, but listen to it. A Geiger counter registers incoming ionizing radiation. What that is, I will discuss a bit more later. Also how the Geiger counter works in particular, I will discuss later. For now, just see to it as a device that records incoming ionizing radiation and produces the signals that you can hear. Each one of the blips that you can hear is one single particle registered by the detector. Let's listen to it a little bit longer. From the sounds that you hear, you can draw a number of very interesting conclusions that tell you a lot about radiation. In order not to disturb the discussion and you're listening too much, I will switch off the signals for a while. So while you cannot hear the signals, of course there's still radiation around. The Geiger counter just makes them audible to us. Otherwise radiation is around us and we cannot really see it or feel it. What I had here in front of the Geiger counter is a mineral called autunite. It contains uranium and the decay products of uranium. That's why it has the signal here also saying that it's radioactive. It's a very interesting and nice mineral that you can find in certain mines. And it sends out different kinds of ionizing radiation that are registered by this Geiger counter. Now, if you listen to it, then what you heard is just a number of blips, not evenly distributed in time, an important point I will come back to later. The kind of blips were always the same. There was no indication, there was no information about what kind of radiation it is or what energy it carried or any other kind of information, just that a particle was registered. It is a very sensitive device because just a single particle can lead to an audible signal that you can hear. A single particle that could be a photon, for example, a high energy photon, so-called gamma radiation, or some other kind of ionizing radiation. So if you listen to it, and I said it just a few seconds ago, it was not evenly distributed. There was not a distinct rhythm to it. It was more like a kind of noise. And I can switch on the detector for a while again. And you can hear it just is random noise. There's nothing particular in the sequence of the signal. It's just random. And if I remove that or put it further away, then it gets fewer and fewer counts. And if I put it very far away, then eventually, if I put it very far away, I'm only sensitive to so-called background radiation, for example, emanating from my body and so on. So if I put it closer, we can hear this randomly incoming particles, randomly incoming ionizing radiation. Let's switch it off again, not to be disturbed too much. And what I want to emphasize now first is, except for that it's not really distinguishing between different kinds of particles and so on, there are other detectors that can do that. More elaborate one that can give us a lot of information about radiation qualities, direction, and so on. It's just this randomness. What does this randomness tell us? This is actually one of the most fascinating features of listening to a Geiger counter. This randomness is something that was very hard to understand early on. It was a major discovery more than 100 years ago, that decay, that is the origin of ionizing radiation, that radioactive decay is something that happens randomly. You can do statistical analysis on that, but you cannot, by looking, for example, at a single nucleus, tell when it is going to decay, when it is going to send out some particle. It's just a random thing, a statistical thing. This is something that was at odds with the picture one had of physics some 150 years ago, where everything seemed deterministic. If you think about mechanics, for example, if you think about planetary motions, the goal or the objective was always you look at where a planet is at a certain point of time, and then you can project, by following the laws of gravity and so on, where it will be at any time in the future with very high accuracy. Same thing holds for other disciplines within physics. You can predict sort of the future by knowing what is currently the case. Even if you think about thermodynamics, for example, something like gases and so on. Of course, there's a large number of particles that interact that makes it all look random, and you need statistical methods to treat thermodynamics. But nevertheless, if you have a volume of gas at a certain temperature, for example, you would know the position of each of these particles at a certain point of time, it would seem that in principle it should be possible to see where these particles are after a certain amount of time by just following how they move, how they bounce around, and everything would be deterministic. Now, this randomness is really at odds with that, and this was one of the founding discoveries of what we then call quantum mechanics. There's a randomness in nature, something that you cannot really predict. You can only on average say on principles, on first principle, not because of limited knowledge like in the gas example, but really on principle, on fundamental principle, you cannot determine when a certain nucleus will decay. If you have a certain amount of nuclei, whatever you have, for example uranium, in this case it's mostly uranium-8, uranium-238, you can say with a certain probability how many will decay in the next time interval. If you have an amount of nuclei and you can have something that decays with a 50% probability, say in the next 1 minute, then this is what we call the half-life of that nucleus. It has a half-life of 1 minute if after 1 minute half of it has vanished. So it sounds rather obvious. So the point is, in the statistical observation that we just listened to, that this probability will always be the same. There is no memory. Or to put it another way, nuclei do not age. They do not remember that they have not decayed the last minute. So after 1 minute has passed, the survivors, they still have a 50% probability of decaying the next minute if the half-life for that substance is 1 minute. So after 1 minute you are left with 50% of the original nuclei. After 2 minutes is 50% of that 50%. That means 25% of the original amount, and so on. And what you would get then, if you draw a curve on how much is left after a certain amount of time, is something like that resembles an exponential decay. And that is the law of decay that you can find in textbooks, and you can read more about. So just by listening again to this randomness, you can draw this kind of conclusion, and you can say that something has a half-life and something will decay, and you can describe the number of nuclei with an exponential function. That means, for example, if you have 1000 nuclei with this assumed half-life of 1 minute, that after 1 minute you have 500 left. Of course not exactly 500, but something close to 500. If you have huge amounts, you can say it's half of it, but again there's a statistical distribution about what survives and what doesn't. And that means if you look at a single atom or a single nucleus that is decaying eventually, you cannot really say when. You can only say with a certain probability within the next observing interval it will decay or not.